Hey guys, welcome to another exciting physics lesson. So this time we're going to be looking at buoyancy. So the idea of buoyancy is awesome because we can figure out what it's going to take to make a huge thing that seems like it shouldn't float. The idea of buoyancy actually comes from way back when, back in the early times. There was a guy named Archimedes, so a Greek dude, and he actually figured out this idea of buoyancy. And so the idea of buoyancy is this. When you have some water right here, and you put something in that water, okay, that water actually, the level actually goes up, overall of that water. So what's actually happening is the boat is pushing the water aside, and the water is then what we call displaced. And here's what Archimedes figured out. If you are to actually take, and so this is the volume of the boat that's in the water here. If you were actually to take the volume of the displaced water, right? And you know the density of water, and then you also know the amount of weight that goes down. As long as this volume of water that's been displaced or pushed aside has more force or more weight than what's pushing down, it'll float. And so that explains why we've got ships like this. What is this stuff made of? This is all metal. There's concrete on this ship. I mean, there is just an enormous amount of weight on this boat. And it's all made of things that you wouldn't think of as floating things, like metal and concrete and things like that. But yet, it floats. And it doesn't float because there's some gas inside here. It floats simply because the shape of the bottom of this pushes aside more weight in water than this whole boat weighs. And so it seems incredible, but it actually is the way that it works with buoyancy. All right, so let's take a look real quick at this idea of buoyancy and kind of do a calculation. So when we're looking at buoyancy, buoyant force. So we have buoyant force, A right there, actually is going to equal then essentially the force that's created by the water. So remember, this was our boat in the water. So it's going to be the force that is created by the water pushing up, which is a result of whatever was stuck in it pushing the water aside. So the buoyant force is going to be a counteractive force to what is coming down. And so we calculate it by the density of the fluid. So if this is water, we would use the density of water. Okay, so the density of the fluid that it's in, and so this means you could actually calculate buoyant force for anything, as long as you know the density of it, times the volume. So we would also times the volume of the object that's in the water. So we're going to need to know the volume of this right here, times gravity, because that's the force that's pulling down. Okay, and so then it's going to have an opposite force down from that. So this is just a quick little equation to figure out the buoyancy of anything that is stuck in water. So let's think about this real quick. So let's say that here you are. Let's say that here you are. I'm going to let's say that you got your hands up because you're floating along, and you're like, woo! So you're floating on the water. Here you are, floating on the water. And so the idea is, what is the buoyant force? Well, you know the buoyant force is going to be greater than your force pushing down. And how do you know that? Well, you know that because you're floating. Once again, as long as this buoyant force exceeds the force of whatever it is going down, you will float, which is what they have to figure out with a large boat. They just have to make sure that the buoyant force is greater than the force of all this stuff going down. Okay, so let's figure out why you're floating, or basically, let's see. Let's figure out how much of the volume of your body is going to be underwater. All right. So what do we need to know in order to figure this out? Well, we're going to need to know the buoyant or the buoyant force, and then the force of gravity that's on you. So let's say that your total force of gravity, if we multiply force of gravity times your weight, is 610 newtons. Okay. What's it going to take to keep 610 newtons up, and how much volume is that going to take? So we want the buoyant force to counteract 610 newtons, and so that's going to equal. Let's see. So that's the buoyant force right there. That's going to equal Sorry about that. So we've got it's going to equal the density of water, which is 1,000 kilograms per cubic meter, right? Times the volume, which is what we want to figure out, how much of you is underwater, times 9.8, which is going to be the force of gravity that's pulling you down. All right, so it's pretty simple to solve. Basically, let's divide this by 1,000. So we're going to end up with 0.610 is going to equal V times 9.8. So we'll divide that again by 9.8, and see, we end up with the volume equaling, let's see, I'm going to round this correctly, so 6.2 times 10 to the negative second cubic meters. So not very much volume, actually. So not very much of you is going to be underwater. If you wanted to, put this in, so you have cubic meters right here, you could say that. I put it in that form because it's a little bit more accurately expressed right there. Well, there you go. So that is the actual volume of you that's going to be submerged if you're floating, because you know that your weight is being counteracted by the buoyant force because you're up. So this is the volume that it takes in order to do that. All right. So let's go ahead and think of another sort of example here, and this is a thing that we call apparent weight. Now, apparent weight is always basically what you're weighing when some other force is subtracting from it. So if you're underwater, let's say that you're swimming underwater and you come along and it's like you're underwater here and here's the bottom. And lo and behold, there's a treasure box. Woo, you find a treasure box. So what you do is you go up in your boat here, all right, and you're up in your boat, and you say, I'm going to go ahead and I'm going to haul this treasure box up. And so you've connected a rope to it. That's what you did. And you went up to your boat, and you're like, woohoo, treasure. And so what you're going to do is you're going to haul that treasure up. Now, here's the idea. That treasure is sunk, right? But it still has buoyant force on it. So it means that there's still the force of the displaced water from the treasure box pushing up on it, right? So that means it's going to be lighter than it normally would. So the apparent weight is its normal weight minus what the buoyancy is going to do to it, right? And so let's go ahead and figure that out. And so that would actually be, if you were to figure that out, then the apparent weight is actually going to be then the tension force, because you're pulling on this with a string. So this is going to be the tension force that you have to put on that string in order to pull that box up. So let's say that you happen to know that this amount of treasure is going to have a weight of 1,250 newtons, right? So what's the tension force going to be? So the tension force is going to equal right? That weight, which is the normal weight, if you had it out in the air, it would take you 1,250 newtons in order to pull that out. So we have 1,250 newtons, and what we want to know is what is the force of buoyancy going to? Oops, it should be a U there first. What is the force of buoyancy going to do to that, to subtract from that? All right, so let's go ahead and do that. So 1250 newtons minus, so the force of buoyancy, we're going to need the density of water. So once again, it's 1,000 kilograms per cubic meter. And then that's going to be times the volume. And let's say while you were down there, you went ahead and you measured the box, and I could give you those measurements, but let me just skip that and just say that you figured out that the thing's volume was 6.5 times 10 to the negative third meters cubed. So we need the volume, because remember, force of buoyancy is going to be the density of water times the volume of the box times force of gravity, which is 9.8, because the Earth is still going to pull on it no matter where it is in the water. All right, so so here we are. So let's go ahead and multiply this out and subtract it. And when I subtract that from 1250, I find that my apparent weight is 1.09 times 10 to the third newtons, which means that it's gone to, so 1090 newtons. So the force of buoyancy has subtracted a pretty decent amount of weight from this thing, right? And so even though it's kind of a little box overall, it weighs a lot less. And you guys may have noticed this, where things underwater weigh less than they do on top of the water. And why is that? Well, it's because of this idea of buoyancy. And so buoyancy subtracts from its normal weight and gives you a new weight, which we call apparent weight. So apparent weight equals your force, your normal force, so basically your mass times 9.8, whatever it is, minus the force of buoyancy, right? Which is the density of the fluid times the volume of whatever's in it times 9.8. So there you go. So you could always easily figure out your apparent weight, or what something's going to weigh underwater if you know these things, or if you know the apparent weight, you can solve for each one of these things individually. All sorts of awesome stuff. So, so this is kind of how we figure out buoyancy and how we figure out apparent weight.